So in part 3 of this set of lectures, we're going to talk about titering, or quantitatively measuring the number of phages in a lysate. So a couple of things to remember before we actually begin this. First, we want to recall the metric system. Right? The metric system is a system of measurement. We have a number of different units for measuring different things. We have meters to measure length, we use grams to measure mass or weight, and we use liters to measure volume. An important aspect of the metric system is that it's organized into powers of 10. We use these prefixes such as milli, micro, and nano to indicate units that are smaller than the base unit. For example, if we're talking about milliliters, we are talking about 1/1000th of a liter. We're going to work with small things, and so we're going to focus just on these small unit prefixes, particularly milli, micro, and nano. Milliliters are 1/1000th of a liter. Microliters are 1/1,000,000th of a liter. And nanoliters are 1/1,000,000,000th of a liter. An important thing to recognize about the metric system is that it's arranged in powers of 10. Right? So it's pretty easy to multiply and divide by 10 because we simply add zeros or subtract zeros. For example, if we multiply 29 by 10, we get 290. We just move the decimal place to the right, add a zero to that number. If we divide by 10, for example, if we divide 29 by 10, we get 2.9. We simply move the decimal to the left. Milli, micro, and nano units are 1,000 times apart from each other, which is also an easy unit to divide once you get a little bit of practice. We use these scientific notation multipliers, which is a convenient way to write and represent these powers of 10. So 10 to the first power is just something times 10. 10 to the second power is 10 times 10, or 100. Let's talk about these exponents for just a little bit. I think people get caught up on them, but it's really a lot easier than you think. Okay, so an exponent just means we multiply a number of times. So we have 2 to the second, and that's the same as 2 times 2, which equals 4. We have 3 to the third, and that's the same as 3 times 3 times 3, which is 27. If we have 10 to the second, that means it's 10 times 10, which is 100. And for powers of 10, we can just keep track of the number of zeros on this number. Right? So 10 times 10 is 100, which is a 1 with 2 zeros on the end of this. 10 to the third is 10 times 10 times 10, which is 1,000, which is a 1 with 3 zeros on the end of it. So negative exponents, first thing you need to remember, negative exponents are fractions, right? So 10 to the negative 1 is the same as 1 over 10 to the first, which is the same as 1 over 10, which is 0.1. Right? Just move that decimal place to the right, or to the left, excuse me. 1 over 10 to the negative 2 is 1 over 10 to the 2, which we just determined is 100. And so that's 0.01. So move the decimal to the left or right, depending if you have a negative exponent, move to the left. If you have a positive exponent, move to the right. So scientific notation lets us write big, or really small numbers without so many zeros. For example, we'll use the unit mole, especially in chemistry. A mole is a really, really big counting number. So 1 mole is equal to 602.216900000000000000000, right? Or instead of writing all that, you could just write 6. This is about 6 times 10 to the 23rd, because there's 23 decimal places after that 6. Right? We'll also talk about really small numbers like a nanoliter, which is 0.00000000001 liters. But you could also just write 1 times 10 to the negative 9th. So we're going to use these numbers to keep track of serial dilutions. So a dilution is when we make something less concentrated. Right? So if you dilute some Gatorade in water, you get a drink that is less sweet, less red, less sugary. So if we do serial dilutions are stepwise dilutions where we make usually the same dilution multiple times in the same way. In this class, that step is often going to be dilutions of 1 in 10. A dilution factor is the total dilution of a sample compared to the original. We have an example here on the right of a bacteria culture, a culture with a whole bunch of bacteria in it that is being serial diluted in order to spread it on a plate. So there are billions of bacteria in this sample. If we take 1 milliliter out of that, very concentrated, turbid, cloudy sample, and put it in 9 milliliters of sterile broth, we'll get a slightly less cloudy solution. If we spread that, we still see there are a number of bacteria, and so if we spread it on a plate, we'll get a whole bunch of bacterial colonies growing on that plate. But if we do another serial dilution, so if we take 1 milliliter of that more dilute solution and dilute it in 9 milliliters of other liquid, it gets less cloudy. We still might see a whole bunch of bacteria. But if we do that again, right, we take 1 milliliter into another 9 mils of sterile water, we can start getting single colonies. If we do it again, we'll get fewer colonies. And if we do it again, we'll get even fewer colonies. So every time the number of bacteria, the concentration of bacteria in the sample goes down. And the dilution factor each time, because we take 1 milliliter and make a total 10 milliliter solution, is the 1 plus 9 equals 10, right? We're diluting this 1 milliliter into a total volume of 10 milliliters. Right? It's 1/10 as concentrated as it was the previous dilution. Right? So the dilution factor here in this first tube is 1 in 10. The dilution factor in the second tube, because we took another 1 in 10 dilution, is 1 in 100, or 10 to the minus 2. The third tube is 1 in 1,000, or 10 to the minus 3. Third tube, it's 1 in 10,000, and so on. You can think of serial dilutions in a number of different steps. So if we went back to this example of a sports drink, if we took 5 milliliters of a sports drink and diluted it in 5 milliliters of water, right? That sports drink is going to be half as concentrated, half as red, and half as sweet as it was the previous time. And the dilution factor is 1/2. If we take 5 milliliters of that dilute sports drink and dilute it in 5 mils, it's going to be diluted again, half of what it was the previous time. So now the total drink is 1/4 as sweet and as concentrated as it was in the original sample. So here's some practice, some 10-fold serial dilutions. Making a number of serial dilutions, 1 mil into 9 mils of sterile buffer. What's the dilution factor of each one of these tubes? A, B, and C. So to figure this out, go ahead and count the number of serial dilutions. So this first tube, A, we make a 1 in 10 serial dilution, so the dilution factor is 1 in 10, or 10 to the negative 1. We make a 1 in 100, and then a 1 in 1,000. So B is 1 in 1,000, or 10 to the minus 3. We did another tenfold, so that's 10,000. Another tenfold is 100,000. Another tenfold is 1 million, 10 million. And finally, C is 100 million, 1 in 100 million, or 10 to the negative 8th. So we can use serial dilutions in conjunction with our knowledge of plaques to titer or count the number of virus particles in a phage sample. Right? So we talked before how each plaque starts as a single phage infection. Right? So we have one single phage that infects some bacteria, bursts out into a number of additional phages that kill the surrounding bacteria, right? And continue to expand to make that plaque one single plaque. Right? So if we see a nice round plaque, that means that there was one phage that infected the host. So We don't know if there are phages that might have ended up on that plate that just didn't form successful infections, right? Or if they're dead phages or something else. But we know that each one of those plaques started as a plaque-forming unit. Right? So this is a specific term we're going to use for these phages that cause plaques to form. We use PFU as an abbreviation of this. So titering phages, the protocol for this can be found in the Phage Discovery Guide for 6.2, 6.4, and 6.5. There's a few different ways you can set up this assay, but it all starts with doing serial dilution. So we're going to make serial dilutions of a phage sample first, right? Because oftentimes our phage samples will have way too many phages in them for us ever to get single plaques on a plate. We're then going to mix each diluted sample with some host bacteria and then perform a plaque assay. We want to perform enough plaque assays so we can find plates with a number of plaques that are isolated so that we can count them. We want to count the number of plaques to determine the number of plaque-forming units that were put on the plate when we did the plaque assay. Finally, we want to calculate the PFU concentration in the original undiluted sample using some of the math we just did. So this is the equation that we're going to use to calculate phage titer. We're going to go over the equation, but I want you to think carefully about what the math actually means. For example, here on the right, we have some results of a serially diluted phage sample. We have 10 to the minus 1 plaque assay, a plaque assay with a 10 to the minus 2 sample, a 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, and 10 to the minus 6. So you should observe carefully a few things about these plates. First, on the 10 to the minus 5 and 10 to the minus 6 plates, we have these nice individually appearing isolated plaques on these plates. You notice here on the 10 to the minus 4 plate, which remember is 10 times as concentrated as the 10 to the minus 5 plate, that we see these plaques, but they're so numerous and so overlapping. In fact, there are probably 10 times as many as there are in this plate, that we really can't see or count any of those plaques. See on these top 3 plates that there's so many plaques that there's really no bacteria growing on these plates at all. Right? And you can see how much less cloudy they are than the 10 to the minus 6. So when we calculate the number of PFUs per milliliter, we want to find a plate where we can count a number of plaques. We want to find a plate where we can count between 20 and 200 plaques on a plate. We want a plate that looks like this here, where we have enough plaques that we can get an accurate count, but we don't have so many that they overlap and we can't count them. We don't want to be sitting there all day counting thousands of plaques. We're also going to do this plaque assay with a specific volume of phage sample. We want to keep track of that volume because all the plaque forming units that went into this individual plaque assay, they all came from this liquid that we squirted on the plate. Finally, we want to look into the dilution factor and use that dilution factor to figure out what the concentration with the PFU per milliliter is in the original sample before we did serial dilutions. For example, if we had this plate here, right, you can look at this plaque assay and say, which plate should you count? Which one has between 20 and 200? And it's clearly 10 to the minus 5. You count the number of plaques here, it's actually 23 plaques on this plate. We know this plaque assay was done using the standard procedure that's in the Phage Discovery Guide, and the volume that we use in that assay is 0.01 milliliters of liquid that we mix with the host bacteria. Finally, we did serial dilutions to set up this plaque assay, and the dilution factor for this sample that we counted is 10 to the minus 5. So we'll plug these numbers into the equation. We have 23 plaques, 0.01 milliliters is the volume plated, and 10 to the minus 5 is the dilution factor. And the concentration of plaques in this sample is 2.3 times 10 to the 8th PFU per milliliter. So let's think about where that comes from using this example. And so here on the left, we have a really concentrated phage lysate. You can see it's so concentrated with viruses that it's kind of cloudy like the bacteria that we grow. So we're going to take this very concentrated phage sample. We know there are so many phages in there, we're probably just going to destroy all the bacteria if we use it straight up. We're going to make serial dilutions, and we're going to make a bunch of them. We're going to dilute 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, all the way down to 10 to the minus 8 by mixing 10 microliters of our sample with 90 microliters of buffer in each tube. We're then going to take 10 microliters, or 0.01 milliliters, and mixed it with some host bacteria and spread it on a plate to do a plaque assay. So on this top plate, we have spread out 10 microliters of our 10 to the minus 6 dilution, 10 to the minus 7th, and 10 to the minus 8th. We'll then incubate those plates, have the bacteria grow, so that we can see the results of the plaque assay. So imagine on these plates that on the 10 to the minus 6 sample, we have way more than 200 plaques. It's too hard to count. On our middle plate, we count 21 plaques. And on the lowest dilution, we count 3 plaques. So let's think about these numbers that are going to go into our equation. So which of these plates are we going to use to count? So we're going to use this middle plate. That's the Goldilocks plate. We have between 20 and 200 colonies on the plate. Or, sorry, 20 and 200 plaques. Those plaques were started by a plaque-forming unit, a particle in this sample that we used for the plaque assay, that turned into a plaque when we put it on the plate. Remember, all those plaque-forming units were present in this 10 microliters of sample that we actually used in the sample. Right? And so that 21 PFU was in 10 microliters, or 0.01 milliliters of sample. Right? So there are 21 plaque-forming units per 0.01 milliliters of sample in this plate. But though we know that this sample is actually diluted many times compared to the original sample, we're really interested in what is the PFU per milliliter concentration of this original sample. So we have to correct for that dilution factor. And the dilution factor there is 10 to the minus 7. So we can type that out nicely. And so we again have 21 plaques that we counted, so we have 21 PFU. And that 21 PFU was in that 0.01 milliliters that we put on the plate. And the dilution factor of that sample was 10 to the minus 7th. So those are where all those numbers come from in our equation. We can then do the math, come up with 2.1 times 10 to the 10, or 21 billion PFU per milliliter in this concentrated phage sample at the beginning.